And so let's talk about energy in rotational motion. So in linear motion, what's the kinetic energy? What's the only kinetic energy we know so far? No? I don't know any kinetic energies. I think it's on like the previous slide.
This is the formula?
Yeah.
1/2 mv.
There we go, 1/2 mv squared. Man, it is a rough week. Okay, so let's talk about that. So that means if we spin this thing, and look, it spins. If we spin this thing, all of the pieces on here are moving, all right? They each have a speed and a mass, and so you could do 1/2 mv squared for each little piece of this weird shape, okay? So remember, we have our angular speed. So our kinetic energy is going to be, let's just pick a point on here, just for the sake of it, okay? So here's our point. Our point's going to be a distance r1. So this is mass 1, distance r1 from the axle. So that means we have, and it has a speed of v1, all right? So we know kinetic energy is 1/2 m1 v1 squared, and we know that because we're given omega, which doesn't depend on radius, we can write v1 as omega times the radius, okay? So that means our kinetic energy at this point is 1/2 m1. This is v1 squared, but we want to write it in terms of this thing because what's special about angular velocity is that it doesn't change depending on radius, okay? So we include the radius here, and we include angular velocity instead of linear velocity, okay? So of course, obviously we have to do the whole disk. So let's pick another point, and we could say, okay, for this point, we can write the same thing out. So we get 1/2 mv squared, but it looks like this, okay? So that's 1/2 mass 2, right? Assuming it's a different mass. Then we have this distance instead of this distance, and we have omega again. So remember, r times omega, that gives us v tangential. So this is just 1/2 mv squared, okay? We do it again. Here's another piece, 1/2 mv squared. And if you add all these up, right, you can sort of guess that you could just keep doing this for point after point. Now remember, you're adding up a bunch of tiny things. What does that look like mathematically? Yeah, it looks a lot like an integral, but just for the sake of it, if we wanted to do this, we can pull out this omega because we know it's the same for everything, because omega for any spinning object is the same no matter how far you are from the axis. And then we just end up with these m1 r1 squared terms, okay? And it turns out you can do this as a summation or an integral. We'll get to the integral later. But this thing, right, you end up with 1/2 something omega squared, which looks a lot like 1/2 mv squared, right? It's 1/2 something that's probably like mass, and then something that's like velocity squared. This ends up being the moment of inertia, okay? And moment of inertia, so this is our new rotational kinetic energy. We can write it as 1/2 I omega squared. Moment of inertia is written as I for inertia, I guess. Moment of inertia is the sum of the masses times the distance squared, okay? And remember, mass measures inertia, right? It's the resistance to motion. So I would like the people that are here, and if you're at home, you can join in. Go ahead and stand up. Okay. So put your hands down at your sides. This will look really cool. And then rotate like this, okay? Okay. And then, if you have the space, put your arms out and do it again. All right. Which one was easier? Yeah, you have to use a lot less actual energy to do this than you have to do this, okay? Have you changed mass?
No.
No. So, okay, you can sit down now. It turns out the distribution of mass matters, okay? Things that are farther away from a rotational axis take more energy, more rotational kinetic energy to move. And so moment of inertia is sort of the rotational equivalent of mass, okay? Because remember, mass is the resistance of an object to acceleration. We've been treating everything as points so far, but that's obviously not true. Moment of inertia measures the resistance of an object to angular acceleration, so the resistance to rotation, okay? And it turns out the more mass you have farther away from your axis of rotation, the larger your moment of inertia is, okay? If you're just a stick and you're spinning, that's pretty easy. But if you're like a big disc or anything large with a lot of mass farther out, like a wheel, then you have a lot more inertia, okay, for better or worse. So if these things have equal mass, right, this is going to have a much smaller moment of inertia than this. Right, so given an equal distribution of mass, the farther the mass is from the axis of rotation, the harder it's going to be to rotate. When we talk about conservation of rotational momentum, there's definitely some applications that come to mind. Like, I don't know if you've ever seen figure skating where someone starts spinning and they have the arms out and they pull them in. What happens to their rotation speed?
Real fast.
It gets really fast. It's sort of terrifying. Yeah. Anyway, moment of inertia tells you how much resistance you have to angular acceleration. So less moment of inertia is a lower resistance to rotation. It's easier to get something spinning quickly if it's got a smaller moment of inertia. If it has a larger moment of inertia, it's much harder to get things spinning, okay? And the units of moment of inertia are just mr squared, so kilograms times meters squared, okay? Cool. So here's some typical moments of inertia, and I just want to go through and guess which is going to be bigger between certain things. So assuming these are the same mass, which one would you expect to have a larger moment of inertia? The one that rotates about the center, so like this, right? Or the one that rotates around the end, so like this.
Right.
Around the end, right? And that's because there's more mass farther away from the axis of rotation. Okay, what about, this is pretty much the same thing, just it's a thicker stick. In this case, if these things had the same mass, which one has the larger moment of inertia? The one that is a solid cylinder or the one where the mass is all distributed farther away at the radius of the cylinder? Yeah, the shell, right? So assuming these things have the same mass and it's equally distributed, this one is going to be larger, okay? So and you can see if you actually calculate these, this one is smaller, 1/12 smaller than 1/3, okay? Over here, 1/2 smaller than 1, okay? And we'll learn how to calculate moment of inertia as an integral in this chapter. We also need to talk about rotational mechanical energy. So here's the potential energies we've talked about so far. So this is our gravitational potential energy. This is our spring potential energy. Here's our regular kinetic energy for linear motion, translational motion. And now we have this kinetic energy for rotational motion, okay? Remember, mechanical energy is still conserved if there are no dissipative forces and there's no external work done on the system, all right? And oh yes. So remember, if you have an object like a ball, for instance, if I just slide the ball, what kind of kinetic energy do I need?
Linear.
Just regular linear kinetic energy. So if this ball is just moving like this, it's not spinning at all, then you only use linear kinetic energy. If it's just rotating, what kind do I use? Just rotational kinetic energy. But if I roll it, what kind do I use? Both, okay? So that means it takes more energy to roll something than to slide it to some extent, okay? And we'll talk about that as when we talk about conservation of energy some more. But before we do that, we're going to try, mechanical energy problem. Okay, so we have a meter stick. Oh, it's attached to the wall at one end, right? So essentially we're just doing this. Okay, so we're bringing it up and we're dropping it and we're looking for the speed at the end of the meter stick right before it hits the wall. Okay, and we actually have all the information we need to do this in this problem.
Oh yeah, now my iPad doesn't recognize me. I feel like, have you guys seen Terminator?
I heard it.
Any of them?
Yes.
Like the concept is like, you've seen all of them, yes. The concept is that like robots and machines take over the world and like try to kill all humans. But I really feel like what's going to happen in real life is going to be much more boring, where robots and machines like make our lives more convenient and then inevitably ruin our lives, and we'll just wish for death. Okay, because they're not going to actually kill us. They're not designed well enough. The biggest problem with robots and technology is that they're designed by people who are not good at things. Okay. Yeah. Okay. The only smart thing, the only time I've ever seen a large group project work out really well is like the moon stuff. Like all other like conspiracy theories, like my main problem with conspiracy theories is just that like most people are incompetent. Like having a whole group of people successfully do something and nobody find out about it just seems so unlikely, because there's always at least like one dumbass in the group project that ruins everything. And so just having a whole group with no bad people that suck is basically impossible. And so that, yeah, things to look forward to in work is like almost all jobs are a group project, especially in engineering. So, join the workforce and realize why conspiracy theories are dumb. Also, just try to keep a secret with like more than 3 people. That doesn't work either. All right. Cool. So let's talk about having a bad day. Let's talk about conservation of energy. We have this meter stick. Do you remember that part? That was like ages ago. Okay, we have a meter stick. It's attached to a wall. It drops. Cool. All right. We want to know the speed of it right before it hits the wall. So, oh gosh, there's something in the chat. What could it be? Oh yeah, sorry about the TED Talk, Jason. I'll just go on another rant if anything else goes wrong. Cool. So let's draw this. We'll do the before and after, because that's always how we want to do our initial and final states for our energy system. So here is our let's just draw our wall. Here's a wall. Here's some shading to show that it's a surface. And then we're going to have a meter stick. This is the initial position for our meter stick, and then this, I'm going to just draw it in a different color. This is going to be our final position for our meter stick. It's not a good drawing, but whatever. And I'm going to shade it in because why not? Okay, so initial, and the other one is final. The things we care about, remember this, because this thing is moving, this is going to be V initial, which is equal to 0. And at this point, we'll have V final, which we're solving for because that's what we care about, because we're asking what is the speed of the tip of the rod as it hits the wall. So right here at radius 1 meter, okay? Other thing we need to care about that we just learned about is the center of mass. And the center of mass of this meter stick should be in the middle, because we just did that integral to figure that out. But also, you guys know that the center of mass of a meter stick is in the middle, all right? Unless it's a really weird one that's really heavy on one end, okay? So we know that we have a mass of 200 grams, but we want that to be in kilograms. So that is 0.2 kilograms. And we want to know that we want to use conservation of energy. So we're going to talk about our initial energy, and just remember, conservation of energy now has a few different things that we can use. We have 2 types of potential energy, and then we have 2 types of kinetic energy. Right? What are we using here? Like, which of these are the ones that we care about? So which potential energy do you think? Yeah, the first one, right? The gravitational potential energy. And then which kinetic energy?
Rotational.
Yeah. There's a really big hint right here. So rotational kinetic energy. So when we're writing out our equation, at this initial state, what kind of energy do we have? Like when we're up here? Potential. So when we write this out, we start with mg, let's say y. Okay. And then what kind of sorry. And then do we have any kinetic energy? No, it's not moving. We're letting it go from rest. Okay, at our final state, do we have potential energy? No, but we do have kinetic energy, and that's going to be 1/2 I omega squared. Okay, stop laughing at me. I will end you. Okay, so, whew. All right. So what's our y? How far is this thing falling?
A meter.
Is it?
No.
No, because what part of the meter stick do we care about for potential energy? The center of mass. So the center of mass is going from here, right, to here. What's this distance?
15.5.
Yeah, 0.5 meters, so 1/2 meter. So our change in y should be 1/2 meter, okay? Because this is a rigid object, so we care about the motion of the center of mass, okay? So we'll rewrite this as m. We'll say this meter stick is m. I'm gonna make that a capital M, just because this is written as capital M. G, y, we know y is going to be 0.5 meters. When we can plug in our I, our moment of inertia, it's given to us right here. That's 1/2 m L squared. What's L in this case? The length, yeah. And so we're gonna first calculate omega, and then we're gonna use that to calculate V. Okay, because V is what we actually care about. But remember, how do we relate back and forth between omega and V? Yeah, V is going to be R omega. And in this case, R, because it's saying the tip of the rod, that's going to be 1 meter in this case. Okay, so keep track of, some of these will be 1/2 meter, some of them will be a whole meter. And we can already look at this equation and cancel our M's, okay? And we're just solving for omega. So omega is going to be 4 GY divided by L squared, and we're going to take a whole square root of that. Okay, just some algebra. We'll plug this in. So this is 4 times 9.8 meters per second squared times y. Remember, y is 0.5 meters because we're talking about the center of mass. L is going to be 1 meter. And that's 1 meter squared, okay? And so we plug all this in. That gives us our omega final of 5.42 radians per second. And if we want this to be, oops, that's a weird V. We want this to be V final, which is what we're looking for. We just take omega times R. So that's going to be, omega is 5.42. We multiply it by 1 meter. So what's 5.42 times 1? 5.42 meters per second, and that is our final velocity, okay? So on the one hand, this is pretty similar to what we've been doing, but we've added this extra thing. You just really have to pay attention to things like the center of mass here, so that change in height is no longer 1 meter. It's going to be just the change in height of the center of mass. And then we also now have rotational kinetic energy instead of just regular kinetic energy. All right, cool. So let's go, oops. Nope, don't want that. So remember this thing, right? We can calculate these, and we're going to talk about how to calculate these, but we're first going to talk about something called parallel axis theorem, which is a very nice shortcut.